Howdy, I'm Clinton Crowley, a geologist and a grad student at the University of Texas at Dallas. You're familiar with this map, and you may have seen a map of U.S. surface geology. But how deep is your knowledge of the Earth's crust underneath the continental United States? This is the first of 3 videos about the continental crust the U.S. is built on and the sedimentary basins that lie on top of it. In this video, we'll see a cross-section of the U.S. continental crust through thick and thin. We'll see what geophysics tells us about the shape of the crust and what kind of rocks it's made of. And we'll find out what's going on beneath the crust and its volcanic consequences on the surface. In the second video, we'll learn about the age of U.S. continental crust and how this formed over the last 3.5 billion years. In the third video, we'll learn about U.S. sedimentary basins, where they are, how they form, and the natural resources they contain. We'll concentrate on the lower 48 states in these videos. Hawaii and Alaska are also important, but we don't have time in these videos to do justice to them. Before we look at U.S. continental crust, let's review what kinds of crust Earth has. Earth's outermost layer, the crust, comes in 2 types, oceanic and continental. Our planet's ocean floors are made of oceanic crust, which has a broadly similar basaltic composition and is about 6 kilometers thick the world over. Continental crust, which forms the continents and continental shelves of the world, is much thicker than ocean crust and is made of many kinds of rocks. Geologists say the continental crust has a granitic composition. That's a little oversimplified. Continental crust is not made by one uniform process like oceanic crust. Continents are made of many different kinds of igneous and metamorphic rocks that accumulated over hundreds to thousands of millions of years. Granite and gabbro, slate, marble, schist, and many others. But overall, it has a broadly granitic composition. Younger sedimentary rocks lie on top of basement rocks in basins, broad platforms, and belts of folded mountains. How thick is continental crust? Compared to the whole planet, it's not very thick. The average thickness of the crust beneath the U.S. is about 40 kilometers or 25 miles. Earth's radius is about 6,370 kilometers, around 3,960 miles, so the crust is less than 1% of Earth's radius. 40 kilometers, compared to the Earth, doesn't sound like much, but it is much more than we can drill through. What lies beneath the crust? Below the crust is the mantle, a huge body of dense rock that makes up 2/3 of planet Earth. Mantle rocks have a different chemical composition from crustal rocks. Mantle rock is called peridotite, consisting of iron and magnesium-rich minerals like olivine and pyroxene. In 1909, a scientist named Moho analyzed seismic waves from an earthquake in Croatia. He discovered the crust-mantle boundary when seismic waves from an earthquake arrived at distant seismic stations before they arrived at stations that were closer to the earthquake. Seismic waves travel faster in the mantle than do seismic waves in the crust. Moho realized that much denser rocks lay below the crust, separated from it by the crust-mantle boundary. That boundary is thus appropriately named after him. It is called the Moho discontinuity, or Moho for short. Moho underlies all crust, including the continental crust of the U.S. Nobody has drilled all the way through any continental crust, so how do we know how thick it is? Good question. We use geophysics to examine what's inside the Earth. Geophysics is the branch of earth sciences that applies the principles of physics to understand what lies beneath Earth's surface. Today, many geophysical techniques can be used to study the Earth, including continental crust. A technique called seismic refraction is the best tool for determining the thickness and composition of U.S. continental crust. It can also tell us something about the underlying mantle. Light rays are bent when they pass through a lens. That's called refraction. Glasses use refraction to correct our vision. They cause light to bend as it crosses a boundary into the denser medium of the lens. A pencil looks bent in a glass of water. The pencil isn't bent, but the light waves are. Anytime an energy wave moves into a medium with a different density, either less dense or more dense, it changes direction in a predictable way. That's refraction. Seismic waves are refracted as they move from less dense continental crust into denser mantle. Every variety of rock has a rate at which seismic waves travel through it. That's known as the rock's seismic velocity. Seismic waves, known as P waves, behave a lot like sound waves, so we can better understand seismic velocity by understanding how the speed of sound varies in air versus water. Sound carries quickly through air with a velocity of 340 meters per second. Sound travels 4 times faster through water with a velocity of 1,400 meters per second. Seismic waves travel 20 times faster through continental crust, around 6,000 meters per second, and even faster in the mantle, about 8,000 meters per second. That's a big jump in velocity from crust to mantle, and the velocity contrast makes the Moho easy to see, though acquiring the seismic refraction data needed to see it is a big operation. How does the seismic refraction technique measure the thickness of the crust? Seismic sources like earthquakes or explosions ring the earth like a bell, sending waves of energy out from the source in every direction. Like a blue jay in a bird bath, geophysicists like to make their own seismic waves by splashing the earth with energy from explosions or vibrating trucks. Instruments called geophones, designed to listen for these energy splashes, are spread out for many miles away from the source. Some waves get refracted at exactly the right angle to go zipping along the top of the mantle, the Moho. Geophones hear the noise made by these waves as they propagate away from the source. Data from the geophones provide the distance versus time information that geophysicists need to know the seismic velocity of the crust and of the underlying mantle. With this information, they can also calculate the thickness of the crust. This map shows the thickness of U.S. continental crust. Excluding the sedimentary rocks on top, U.S. continental crust averages about 40 kilometers thick, but thickens and thins in some places. Seismic velocities tell us about the composition of U.S. continental crust. This map shows the average seismic velocity of U.S. continental crust. Seismic waves move faster in olivine-rich mantle rocks than in continental crust rocks that are rich in feldspar and quartz. This map shows the seismic velocity of the upper mantle just beneath the U.S. Moho. Now that we've seen the maps, what do they mean? Let's look at the crustal thickness map first. Where is the thickest and thinnest crust in the continental U.S.? U.S. continental crust is thickest beneath 3 mountain ranges. 52 kilometers thick beneath the Rocky Mountains of Colorado, 50 kilometers thick beneath the Appalachian Mountains of North Carolina, and 45 kilometers thick beneath the Sierra Nevada of California. The thinnest U.S. crust lies beneath the Basin and Range Province in Nevada, Utah, and southern Arizona. The thinnest crust is about 25 kilometers thick, only 16 miles, half that of the thickest U.S. crust. Crust also thins rapidly offshore of the west, east, and Gulf coasts, where continental crust transitions into oceanic crust. Crust is thickest where it has been squeezed to make mountains and thinnest where it has been stretched. What does seismic refraction tell us about the composition of the crust? Let's look again at the average P-wave velocity of U.S. continental crust. How can we use it to understand how the average composition of the crust varies beneath the U.S.? Think of a rock's composition as its recipe. Some recipes make less dense rocks. These rocks have low seismic velocities. Other recipes make denser rocks, and these have higher seismic velocities. Seismic velocities of about 6 kilometers per second are expected for granites, and velocities of about 7 kilometers per second are expected for gabbro. So we can consider average seismic velocities between 6 and 7 kilometers per second to indicate the relative proportions of granite and gabbro in the crust. Seismic refraction studies also tell us that less dense granitic igneous rocks are most common in the upper crust and that the lower crust is made of denser rocks like gabbro and amphibolite. From this map, it looks like the most granite-rich crust is beneath Nevada in the Basin and Range province. In contrast, the highest velocity U.S. crust lies beneath the middle of the country. What about the P-wave velocity of the mantle just below the Moho? Mantle is less heterogeneous in composition compared to the crust. So why is there a range of seismic velocities in different parts of the upper mantle? Seismic waves slow down in hotter rocks and speed up in colder rocks. Composition of the mantle doesn't vary significantly, so seismic velocity allows us to take the temperature of the upper mantle. This map indicates that the upper mantle is hotter beneath the west than beneath the middle of the country. The upper mantle is also warm beneath the eastern and southern coastal states. We can compare this map to the locations where volcanoes erupted and lava flowed in the recent geologic past. These volcanoes and lavas occur above where the mantle is hot enough to melt, producing basaltic magma. In the Cenozoic era, the last 64 million years, conditions were right in the western U.S. for mantle to melt, confirming inferences from the seismic velocity map of the upper mantle. Watch our video, 3 Great Ways to Melt the Mantle, to find out how. That wraps up our story of what one geophysical technique tells us about the crust of the continental U.S. There are many other geophysical techniques that tell us about the crust, but the important conclusion is that this crust and the mantle beneath it shaped our nation in ways that we take for granted today, such as mountains in the west and east, and rich farmland and great rivers in the middle. How this happened is another story, 3.5 billion years in the making, and that's the next video in our series, The Continental Crust of the United States, When and How It Formed. Thanks for watching, and please like and subscribe to the UT Dallas Geoscience Studio YouTube channel for more Earth and space science videos.